Hello, this is Mr. Pillar for ECET 273, Modern Power Lecture number 16. This lecture is on power electronics, the variable speed operation of induction motors, based on Chapter 9 of the Square 9 of DeWitt text, Chapter 17 of the Fardo-Patrick text. The objectives of this lecture are to describe how variable speed drives operate, and describe how an induction motor performs when operating at variable speeds. Well, what is this device? This device is a diode used in high power circuits, just like all the electronic circuits you're used to from other courses. This device impedes flow of current in one direction. So with that in mind, let's talk about some rectifier circuits. Here's a half-wave rectifier circuit with a capacitor to reduce the ripple. Vs shows the input wave of and Vl shows the output across the load. Note the output waveform is the same frequency as the input waveform. And also note the RC constant drag from peak 1 to peak 2. That is the result of the capacitor. We call that capacitor a filter capacitor. Here is a full wave rectifier with a capacitor to reduce the ripple. Vs shows the input and Vl shows the output, just like before. Note the output waveform is now twice the frequency of the input waveform. This configuration allows for a more pure output waveform, which is closer to the V peak of the original voltage. It was able to do that because the way we have the diodes arranged, we're using not only the top half of the input wave signal, but we're also using the bottom half of the input wave signal. Hence the double the frequency, we have double the bumps on the output wave. Again, you still have the RC constant curve, but it's tighter and the ripple is tighter. The filter pulls in a little tighter to V peak. The final configuration I'm going to mention here for the purposes of this lecture is the bridge rectifier. Here's a three-phase version of a bridge rectifier that also has a filter capacitor. In 2 slides, I'll give you a diagram of the waveform in and out. The diodes are all individually forward biased in sequence for each of the phases. It causes the delta voltages between each phase. So the phase to phase. So VAB, VBA, VBC, VCB, VCA, and VAC. As those voltages occur in peaks and valleys, the diodes are individually forward biased to allow appropriate current through. This is a 3-phase bridge rectifier. We can build 3-phase system with individual diodes or a single device like this. The 3-phase input go in points 1, 2, and 3. 4 and 5 output the DC. Obviously a little more compact and a little simpler to lay out. Here's a bridge rectifier output without a capacitor to reduce the ripple. The black lines are each of the 6 phase voltages. Again, VAB, VBA, VBC, VCB, VCA, and VAC. The blue is the DC output with the ripple. As you can see across the top of that, it's pointing to the number of switches that are conducting at a given interval. So 1 and 6, then 1 and 2, then 3 and 2, then 3 and 4, then 5 and 4, then 5 and 6, then 1 and 6, and continue. And then here is the signal for the bridge rectifier output with a capacitor to reduce the ripple. Again, the black lines are the 6 phase voltages. The red now is the DC output without the ripple. This configuration, we can use this as an input to a microprocessor controlled system of a variable frequency drive. Now we need to figure out a way to take that signal and control an output frequency. So now we're looking for items that we can control other features. The SCR is a diode that has a secondary function outside of what a standard diode can do. There's a control signal that can be applied to adjust the phase angle that is allowed through the circuit. This feature allows for automated control on the average value of the output of the waveform. For example, if this is used as a DC power supply, one can adjust the DC output by reducing the alpha angle and increasing the beta angle. So imagine these diodes used in the three-phase bridge rectifier circuit, and then we have the capability of phase angle firing to adjust our peak output. Another device like the SCR is a triac. This device is essentially a pair of SCRs, allowing for delay of both the positive and negative peaks of the input waveform. Transistors will be required to adjust an output waveform. Transistors can be used as silicon relays. Via a pulse width modulation circuit, we can adjust the output waveform and even create a sine wave-like signal or a sine approximation. BJTs, IGBTs, and MOSFETs are all similar devices. Generally speaking, right now, IGBTs are the common device used in the power industry. So, with the IGBT in mind, we're going to use that as a control device. We can pulse width modulate, or PWM, the gate with the lower voltage, notice the 15 volts, to control a higher voltage on the output. So the voltage delta between G and E is the 15 volts. The voltage delta between C and E would be your VL. And so C and E turn on, for the lack of a better term, full on at when you put 15 volts between VGE and VCE, then allow flow to happen. So now we know the components. Here's the idea of how to turn DC back into three-phase AC power. A, B, and C phases are pulled off the center nodes marked on the schematic. The boxes are switches. Let's think of them as IGBTs. And just as the diodes of the three-phase bridge circuit are forward biased in order to allow the waveform to create the correct voltage potentials of VAB, BA, VBC, VCA, CB, V and CA, and VAC, the switches will be controlled via a microcontroller to activate the proper order and create a step waveform that simulates a sine wave output. The next slide has that waveform. The waveforms VAN, VBN, and VCN show the switching circuits. I've included 3 boxes. The blue box shows when VBN is on, green shows when VAN and BN are on, and the red one shows when VAN is on. VAB is a simulated or approximated sine wave that will run a 3-phase AC motor. We can adjust the on time of the phase to neutral voltages to adjust the frequency of the approximated sine wave. This solution is called a variable voltage inverter. So now we ask the question, why use variable speed? Well, here are a list of reasons. First of all, automation. Many modern systems require precise speed control, position, or torque. With variable frequency drive, we can do that. Energy efficiencies. Motors can run a process at an optimum speed instead of wasting power running at nameplate speed. So there are different processes that a certain machine may need to accomplish at different speeds, and with those different speeds we create better efficiency. Simplicity. Can drive a system directly instead of speed regulation using gears, belts, clutches, and other devices. In the idea of simplicity, the large welding machines that I had worked on before in industry, one of the ideas that they were working on was an all-electric machine. Instead of a huge hydraulic motor, we used a direct drive, frequency drive motor to create our speeds. Or we can use this as a soft start. We can limit the starting current at the control and control the rate of acceleration. So variable speed applications would be for the efficiency, like we said, fans, pumps, and blowers. Precision manufacturing would be CNC manufacturing, injection molds, injection spinning, and extrusion. System simplification would be conveyors, hoists, and cranes. Alright, so the induction motor is the workhorse of industry, but it does have some disadvantages. Primary disadvantage of an induction speed motor is it's essentially a constant speed device. Speed will only change a few percent from no load to full. Motor operating point is determined by an intersection of the load curve with a motor torque curve. So in this case, the load curve would be the upturned parabolic looking shape where P1 and P2 are pointing at the cross points. Torque curves are that standard knee curve that we've talked about last week. What would happen if we reduced the voltage on a motor to reduce its speed? Well, these curves show that, and they show the effect on the output torque when the voltage level is reduced below rated of an induction machine. The slight upward slope is a representation, like I said, of the torque curve and motor load curve and motor torque curve. As you vary the voltage, there's little change in power out, but the machine will draw a higher current. Here's a graph of the torque output of a motor with a variable frequency. As you can see, the power out is decreased at lower than rated frequencies and increased at higher than rated frequencies. Again, the parabolic up-shaped curve is representation of the load curve. There is compensation we'll need to deal with the lower frequencies versus higher frequencies. But first, let's look at a completed block diagram of our system. Here's a block diagram of the circuits we've talked about in the lecture. We'll bring in 60 Hertz three-phase power, convert it to a DC voltage, use that DC voltage as a supply to an inverter circuit using switches that create a simulated three-phase sine wave output. The costs are, we have harmonics added to the supply current and voltage harmonics added to the output voltage. The final question would be, can we arbitrarily change the frequency? And that answer is no. At lower frequencies, because of Faraday's law, we will need to decrease the Vout. Voltage over frequency ratio must be constant at less than rated frequency. So this is called voltage over frequency control. When we get to rated frequency, then we have the voltage remain constant. The field in the motor will be reduced as frequency is increased, and so there will be a little less torque out at higher frequencies. Okay, that is the end of our variable frequency drive discussion, and I hope it was useful. Please go back through it, take some notes, ask some questions in class. I am going to do my best to put another video up for the week. If not, we will have just live lecture. Thank you.